It's really a pleasure to be part of this meeting. It's really exciting and fantastic discussion points for the future ahead. I have the great privilege of really leading this last segment of the workshop, talking about aviation and marine applications. And to kind of seed some thoughts along those lines, I do have a very brief slide deck before we get to the main event, which is our fantastic panelists representing different industries in that space. So I will share my screen. And just really as a way of introducing a little bit about myself and the organization that I work in within the larger fabric of Stanford University and SLAC National Lab, how it relates to energy and transportation, and then we'll proceed forward. So really, okay. Thank you so much for confirming, Jimmy. Absolutely. So this is just kind of a big picture, right? The energy landscape is fast evolving, and that's a wonderful thing. If we look backwards to the last 50 years and just keep doing business as usual, that's probably not the optimum for the future ahead. It's a very large market, that of transportation, among many other markets that will be touched on with energy. Energy touches everything. And the way I look at it is pretty simple and straightforward. At the end of the day, we need products. We need fuels for transportation. We need building materials. We need chemicals. We need fertilizers. We need lots of different types of products out there. And a lot of them are really molecules. They're chemicals. And the way that we conventionally get them, I'd like to just really reflect for a moment on how wonderful the industry is as we know it. The energy industry has been tremendous at delivering the molecules that we need, and we as society take what Mother Nature has given us, resources that are typically found underground, and converting them into the molecules that provide for the way of life as we know it, whether it's driving or jets or food that we eat. Really everything, again, pretty much touches energy one way or the other. So as we look ahead, what might we want to do to really transform that future of energy? We need to find new feedstocks of energy, new feedstocks of molecules to, again, make all the things that we need to thrive. And that's not just, when I say we, it's really a global we, and let's recognize that not everybody on Earth has equal access to the energy system as we know it. So we do have a lot of renewables that are coming online, wind and solar and other technologies that are providing renewable sources of energy. And we have a lot of different molecules out there, feedstocks, that we ultimately need to convert to make into things that we need. So again, fuels for transportation and building materials, fertilizers, food, the whole food and agricultural industry. And so what we do at the SunCat Center, and I'm a faculty member both in chemical engineering at Stanford as well as in photon science at SLAC National Accelerator Lab, and serve as director of the SunCat Center. A lot of what we do is really ply our trade on trying to figure out how to do these chemical transformations as effectively as possibly, as renewably as possibly, as sustainably as possibly, to provide the molecules that we need, and then to make use of those molecules in the best way possible, again, to meet our global societal goals. And so this really fits within the theme of what we're talking about here with hydrogen and transportation. It's a big molecule that we put a lot of attention to. And let me just give credit to and acknowledge my many partners in this. We are a very collaborative organization, over 70 researchers, as we integrate theory and experiments to ultimately create this new future ahead and open up new possibilities. So we're very much focused on these chemical transformations, very much focused on catalysis and catalyzing these transformations, and then developing devices and new technologies, new processes that make use of those. And very importantly, we are a partnership between Stanford University and SLAC National Accelerator Lab that really bring different resources, different expertise to attack these very important and challenging problems. So you see a listing of a number of the Stanford faculty that are core to the SunCat Center, senior personnel through the National Laboratory, many different collaborative partners, both inside of our ecosystem of SLAC and Stanford, as well as beyond. And this is really just to give you a framework on how we operate. Theory is, we're a very balanced organization, again, with theory and experiment. So we have a lot of theory guidance, computational modeling, typically at the atomic and molecular level, that really provides some guidance as to how, what kind of possibilities might exist in developing new processes, new catalysts, new technologies. And then we have a range of experimentalists. I am predominantly an experimentalist who synthesize all kinds of interesting new materials, new formulations, new structures. We use all kinds of advanced tools to characterize them, including the tools that you can only find at things like national labs involving synchrotrons, let's say, or free electron lasers, among many. We test things out to see kind of what works and what doesn't. And then feed that right back into theory, and then we wrap it all in a nice cozy blanket of data science as we as we strive to capture all this data and take on new modes, new approaches to understand how what we've learned and how to make things better ahead. So this, in my last slide, I just want to kind of seed the discussion for our particular panel that we've got going this morning here in California, afternoon and evening, perhaps elsewhere. And that is really the future of transportation. And to motivate this, I'm just grabbing a slide, grabbing a diagram that came from fairly recent energy outlook from ExxonMobil. There's many different energy outlooks out there, views to the future. And certainly they all have their own perspectives. But one thing that I've seen where there's a lot of convergence on, a lot of consensus on, if you will, is really the growth of transportation. Really, we're kind of where we're at today and where it's going ahead into the future. There's going to be a lot more transportation. There's many different types of transportation, and the scale is massive. We're talking about, this projected in the future about 23 terawatts of average energy rate consumption across the globe. Currently, we're at 19 terawatts. That's 19 trillion watts is the average rate of energy consumption across the planet. And it's going to go up probably in the next couple of decades. And about 5 of those 23 are coming from transportation. And I think the interesting thing that you see here is that light duty transportation is ultimately fairly flat in this landscape. And the bulk of the growth in energy usage in transportation is going to be in the heavier duty forms, whether it's heavy duty on roads or aviation, marine, rail. We heard a great panel earlier today on rail, and now we're going to turn our attention to marine and aviation. One of the key conclusions from this particular report is that based on the type of transportation, really chemical fuels are going to be important, largely driven by commerce as the globe becomes more of a global enterprise for the consumption and production of products. And some seeding questions here right before we turn to our panelists will be: what energy sources are going to contribute to the marine and aviation sectors, and what role does hydrogen have to play? And what are the needs for hydrogen production, storage, distribution, utilization for these particular applications? And I can imagine that a lot of what we're going to be hearing about today is going to dovetail well with what we heard in the earlier session regarding heavy duty transport. So with that, let me go ahead and unshare my screen. And we can pass the baton to our panelists. So first, so we have 4 panelists today: Rasmus Bach-Nielsen, Amanda Simpson, Jeremy Baines, and Toru Sugiura. And so we're going to start with Rasmus Bach-Nielsen, who is formerly the global head of wet freight at Trafigura and is now currently the global head of fuel decarbonization. So without further ado, Rasmus, please go ahead and, if you don't mind, getting your slide deck going and take it away.
Thanks very much, Thomas. It's a pleasure to participate today. We just spot on. There's a lot happening in marine space, and I look forward to talking a little bit about how we see the future in that space. It's very much around the topic of this conference. Just let me see. Can you see the slides?
They look good.
Okay, great. So just to frame a little bit who Trafigura is and why we are very active in the space around decarbonization. So basically, Trafigura is a huge commodity trading firm established in 1993. We have $147 billion of revenue. We trade about 5.6 million barrels of oil per day. So in today, that's around 5.5 of world oil consumption that we trade daily. We're the biggest LNG trader. Last year, we were running more than 300 ships at a given time, the biggest tanker shipping company operating ships at the time. Huge in the LNG space. We own infrastructure, refineries, terminals. And then last year, we also started power renewables trading and established a $2 billion renewable investment fund. So it's a huge commodity trading house. A key here for us is that we have $61 billion of credit lines. Obviously, there's significant pressure from stakeholders, from everyone, not only employees, stakeholders, shareholders, financiers, everyone. So we have a task, and we have a big task. We trade carbon, we move carbon, and we need to decarbonize our infrastructure. A little bit about our missions, and then you will understand why we're putting our efforts where we are, which is in the regulatory space. Very brief breakdown of our emissions. On the scope breakdown in 2020, you can see that our Scope 3 emissions account for 78% of our emissions. The challenge that we have a lot of ships transporting the oil and the commodities that we trade. And while there's a lot of pressure on all these ship owners, etc., to decarbonize, then the challenge is that we don't have the regulatory framework to decarbonize fast enough. And what is the regulatory framework, and what do we need, and what's the challenges? About ship propulsion today, ships burn MGO, they burn low sulfur MGO, high sulfur fuel, they burn LNG, they run on LPG, but the key transportation fuel as of today is heavy fuel oil. In terms of what the key challenge is, again today, the regulatory framework does not provide sufficient opportunity for the industry to decarbonize sooner rather than later. Just a little bit about global shipping emissions, just to frame it. Shipping accounts for about 2.5% of global GHG emissions. It accounts for 80% of global trade. So shipping is a vital thing transporting our goods around the world. So if we can decarbonize the shipping industry, then we have come far. The good news is it's possible. The technology is there. The key engine makers are bringing forward the propulsion of the future, and I come to what we believe is propulsion of the future, but that is there. It's ready by 2024, 2025. However, a key challenge is the economics. Everybody say that they want to decarbonize. The ship owners who we have as 78% of our emissions saying they want to decarbonize, but numbers does not work. So if we go a step back in 2019, we initiated a study with a leading American university, unfortunately not Stanford, but that will be the case in the future, I believe. And one of the key conclusions from this study, which took a half a year between them and us, was that the transportation fuel of the future is hydrogen-based. So to answer one of your questions earlier, Thomas, that you put up, what energy sources can be the transportation fuel of the future? We are certain the transportation fuel of the future is hydrogen-based. When we say that, we mean green methanol and green ammonia. Professor Prince, early on in his opening remarks this morning, he said, well, what is the best hydrogen carrier? We believe the best hydrogen carrier is green ammonia, is the cleanest. We come to what we see of the emission profile from that. We're not excluding, and we see that, of course, technology can improve over time. For sure it will. The question is, will ammonia fuel cells become the future? Scientists will determine that in the future. But before we get to that point, we need to get the regulatory framework so you cost neutralize the use of low and zero carbon fuels. After we came to the conclusion last year in 2020 on transport fuels of the future, we brought forward a regulatory proposal for an IMO-led global shipping industry decarbonization program. And what is the IMO? IMO is it's a UN body which was founded in 1948 and is the body that governs global shipping. We believe regulation has to be on a global space and not on a regional space. What is happening today in the EU is that EU ETS scheme is being discussed, and there is a proposal that will be brought forward, we believe, by June 21. The Commission have said they will bring forward a proposal, so we expect that. The challenge with regional measures is that shipping is global, so it's going to be hard to police and to implement and implement this in a regional basis. Thereby not said it's not impossible, but it's difficult. But we believe it has to be done global. And IMO, we believe, is the right place to do this. So how does such a proposal look? Before we get to that point, just a little bit about IMO targets on shipping and how the industry needs to decarbonize. The initial IMO strategy is to reduce total annual GHG emissions by 50% by 2050 compared to 2008 levels. We challenged the fact that it's 2008 levels because that's where everybody was going full speed. That was the end of the last super cycle, commodity super cycle, that I think we all remember very well. These targets, unfortunately, for the industry players, whether that's the ship owners, the charterers such as Trafigura, the oil majors, these targets, unfortunately or fortunately, are not aggressive enough. IMO, thankfully, is in the process revising the emission reduction targets because they are also starting to understand that the pressure from society is building month by month, if not even week by week, which is great because it's pushing our industry forward to do something. However, to do something, we need to get through a highly complex and bureaucratic IMO. Yeah. So we need targets to be revised. It's happening, but then we also need a regulatory framework to change the fundamentals of how the industry can go and invest into low and zero carbon fuels. Last year, we brought forward our IMO shipping proposal, which was the first one. About the IMO, it's a highly bureaucratic organization. There's 174 member states. It's consensus driven. There's a lot of politics involved. You have a lot of small island states which are afraid of higher transportation costs. You have commodity exporters such as some South American countries, I will not mention, who are afraid of having increased exporting transportation costs, thereby making their commodity uneconomical. So there's a lot of thoughts that needs to be put into mind when you need to get through the IMO with a carbon level proposal. We calculated that we need a levy of $250 to $300 of CO2 equivalent, dollars per CO2 equivalent emissions. This is likely to come down over time as electrolyzer technology improves and as the industry uptake of zero propulsion ships becomes the norm. What has been important for us, and we believe for the industry, and we are very engaged within the industry in various associations, etc., in terms of understanding what does it take and how can the industry see itself make this happen and support a carbon levy. Probably for the first time right now in history, do we have all players in the industry asking to be regulated. It certainly chartering traders have not asked to be regulated before, but this is simply because we need the regulation to cost neutralize the low and zero carbon fuels. Before I go to our proposal, just a bit about the pricing of fuels. Today, there is billions of pension fund money ready to invest in renewables. That's a fact. We see it. We have a 2 billion renewable fund ourselves. We're in projects. We see a lot of companies ready to invest in hydrogen. Yeah. And it's there, it's everywhere. There's shareholder pressure on the oil majors, etc. It's coming and it's there. The money is there. However, when pension fund goes and invests for all these renewable projects, you need off-takers. That could be Trafigura, it could be others. The off-takers are there, but the challenge that they have today, and this is for projects that needs to be concluded within, let's say, next 12 months in order for material or the commodity to be there by 25, 26, 27, you need to have demand. But in order to have demand, you need to have regulation because the cost difference is so significant. Let's say for green ammonia today, on forward basis, if you are to conclude that, which the pension fund needs to make the renewable investment viable, you need to pay between 450 to 500 euros on a 10-year offtake contract. The calorific value of green ammonia is 2.2 times less the transport fuels as of today. So you're way off on the economics. So how can you bridge this? It's very hard for companies when trading margins are 1%, about historically 1 to 2%, to go and subsidize such a significant transportation increase. And when you can't competitively do that, and when you don't have an equal level playing field, it is just highly likely that you will delay the implementation of the low and zero carbon fuels. And the ship owners, they will be looking at the fuel is not there, we will not buy in the retrofitting of the ships, and it becomes chicken and the egg. However, if you have regulation, well, then you clear the problem, because then both the pension funds can invest and the ship owners can go and invest in the retrofitting of the engines. And the engines are there. It's an upgrade of the two-stroke engine that we see today. The ammonia, as an example, is toxic. It's being traded today. It's a transported commodity as of today. So it is possible. And this is the great news. Technology is there. So we can see the transition within the maritime space. But again, we need the regulation. And what does it take to make it happen? We believe it's important that funds that are collected from the industry stays within the industry. So what we have proposed is actually inspired from the California low carbon fuel standards, where we have suggested to make an emission profiles of all transportation fuels. And again, there's not that many fuels. I mentioned most of them in my intro. You penalize when you use ships above a certain standard, and you subsidize below the standard. And in that way, you will be whole clean in terms of cost clean, in terms of it will not cost you money when you go and you use the lower and zero carbon fuels. So we believe by far the most funds collected from a carbon levy should go back into subsidizing the use of low and zero carbon fuels. And that will encourage investments, and that will encourage offtakes. Whereas right now within the IMO, there is a group which believes that it should go to funding of R&D. The challenge we have with that as a big industry player is R&D will benefit technology providers, and it will not encourage the industry to go and change behavior because they see zero of these funds if it goes to R&D. We acknowledge that R&D is important. We believe there is a clear trajectory of what the transport fuel of the future will be. Of course, we cannot be certain because technology is changing and it's going fast. We acknowledge that. But we believe only a small portion should go to R&D. And then in order to be practical and to reach decision-making capability, which is consensus within the IMO, we also support for small island states and potentially big exporters who get seriously, they lose competitiveness when transportation costs significantly increases. So that's sort of the key framework from our proposal. And thankfully, it has received very strong attention. If you go back to 2013-14, there was a proposal within the IMO for market-based measures, such as carbon levy. It was turned down immediately. The challenge IMO has now is that a lot of member states, they remember this. So they're saying, okay, we don't believe it can happen. We even have a climate ambassador from a Scandinavian country 2 months ago saying carbon levy will never happen. I was personally crossing my toes. I was shocked. No ambition, no dynamic, very sad, but it can happen. And now the small island states who we've been working with separately have brought forward a proposal at the next MEPC meeting, Marine Environment Protection Committee, which is the governing IMO meeting, where a proposal for a carbon levy is now to be discussed in June this year. That's fantastic. So one of the key challenges that IMO member delegates they have is that you have climate ministers, transport ministers who say we want to decarbonize. However, one of the challenges we see, and we participate in a lot of discussions with NGOs, with World Economic Forum, various organizations that ask for our participation. We see politicians talking, but we don't believe that they truly see what it takes to change. And what it takes to change, again, is the carbon levy. And the transport and the climate ministers can actually go and push the IMO member delegates, and they need to do it. But they need to understand what they need to do. And we're working in the Getting to Zero coalition, one of the many coalitions, which is World Economic Forum run together with Global Maritime Forum. We have a target on targeting these ministers for COP26. And we are very hopeful it's possible. But even 2 months ago, a lot of people were very pessimistic. But again, we need the regulatory framework in order to make this competitive. Again, just a little bit about how we intend to do it. And the slide here, again, define the intensity benchmark. We set the energy intensity profiles, calculations comes out. You have high carbon and low carbon fuels. Within the industry, there's another initiative, which is Sea Cargo Charter. The Sea Cargo Charter makes ship owners responsible for reporting the emissions for each voyage. This is a new charter which has been established in October last year. It's great. There's no global accountability measurements on shipping today. This is for the transport industry, dry bulk, tankers, gas carriers. Container industry is looking to have a similar equivalent implemented. It's not yet there. But by having the Sea Cargo Charter reporting, suddenly we are in the process, I'm co-chairing that, we are in the process establishing a global reporting tool where we actually have data, and also we're getting reliable data. And companies are becoming reliable on an apple-to-apple comparison basis on what we have used in the past of ships and what emission profiles they have. My last slide, and I can talk for a long time, just a little bit about why we believe green ammonia is the transport fuel of the future. The CO2 emission saving is huge. It's what we have, and it's an about figure, about 93% compared to today's transportation fuels. Green methanol is less. There's a carbon content. There's a challenge for the shipping industry. Should we overtake green methanol and burn the carbon and overtake other industries' problems? Or should we just go to green ammonia, which is the cleanest transportation fuel? We believe it's green ammonia, but we are cognizant that green methanol has a chance if you can get carbon capture. And the question is, how will that carbon capture look? And that's again for technology providers to determine over time. But again, the good news, shipping can decarbonize. It's not as unrealistic as it was. There's a lot of positive momentum. We need it to happen. It can happen. And huge corporations, including our own, actually hopefully will be given a chance to choose between low and higher carbon ships sooner rather than later. Thank you very much.
Outstanding presentation. Thank you so much, Rasmus. Thank you also for those of you who are putting questions into the Q&A. We are registering them, and we will handle those at the end of all the presentations. So let's see. So let's go to our next speaker is going to be Amanda Simpson. She is the Vice President for Research and Technology at Airbus. Amanda, how are you doing there?
I'm doing great. Good morning or good afternoon to everyone. Thank you, Tom, for having me. And let me go ahead and share my screen, and hopefully you can see that.
Looks good. You're ready to rock.
Okay, good. Great. I'm gonna do my best to get through as quickly as possible because I'd like to reserve as much time for Q&A at the end. And I believe the charts are going to be available for participants who want to look at them later. So this is a chart from the Air Transport Action Group that was put out late last year. And this is what the carbon emissions from aviation look like and our projections forward. What you see is the dip due to the coronavirus, but then you see as air travel returns, the top line is if we do nothing, here are the continued emissions based upon about a 3.5 to 4% growth that we've seen historically, less the reductions due to newer aircraft that are more efficient than the aircraft that they're replacing. But if we're going to meet the industry goal of 50% reduction based on the 2005 emissions by 2050, you can see we have to do something. Today, that's being looked at, using offsets. Airlines are buying offsets to bring that down. But we see in the future, as more and more sustainable aviation fuel becomes available, that will be used in the current fleet of over 13,000 airliners worldwide. But that's only going to be a portion of the solution. Operations, and I'm going to talk about all these in a little bit more detail. Operations will account for about 8%. And then the remaining, the 40% is as new technology are introduced into the next generation of aircraft. And if we start on the designing that next generation of aircraft today, we can get them into service by the 2035 timeframe so that they can have an impact by 2050. Now, one of the things I am going to point out is that the industry 2050 goal of half of 2005 emissions is the current goal. But there's a lot of discussion about making that goal zero net emissions by 2050. So that puts more emphasis on those components. All right, so moving on, real quick about sustainable aviation fuels. Sustainable aviation fuel, rather than using petroleum, you use other feedstock, whether that's environmental, industrial waste, food byproducts, cooking oil, or even agricultural products, whether it be corn like methanol or a variety of different feedstocks. And you can use that in today's single aisle aircraft, and of course our twin aisle aircraft, wide bodies, and as a direct drop-in replacement for fuel. All modern aircraft are approved for up to a 50% blend of the various biofuel and sustainable aviation fuel products. And there have been over 250,000 flights and counting. It's probably well over 300,000 by now that have some portion of their fuel mix comes from SAF. And that's going to be a huge impact, because it's about 85% of the reduction is right there by using these closed loop. You pull the carbon out of the atmosphere, you put it into the sustainable aviation fuel. The operations is going to be another part. And I talk about how automation is going to really help us out. And I've just got a few real quick examples here. And while, a lot of it has to do with routing. How do we make sure that an aircraft, once, it's ready to do its flight, has the most optimized route for its emissions, right? Taking into account weather, taking into account other traffic, taking into account winds, optimizing that so that when the aircraft starts its engine, it's going to be able to taxi right to the end of the runway, take off, climb unrestricted to altitude where it's most efficient, and as it approaches its destination, stay at that efficient altitude right to the point where it can make a low power, low emission descent, land on the runway without having to hold, without having to divert, and taxi to an open gate without their engines running. So that's where automation, big data starts coming in, handling the thousands and thousands of flights every day. And another thing we look at is how do the aircraft themselves operate? And we're working on automation inside the aircraft, inside the cockpit, because we believe automation can manage the aircraft better than a pilot can, than a human person, and optimize power settings and even trim configurations and all the other settings in an aircraft to reduce their emissions. And we also look at making sure that when an aircraft gets to its destination, it's going to be able to land. So advanced onboard landing systems that use vision-based and other sensors to ensure that the aircraft is going to be able to safely land at that runway in any weather conditions, regardless of whether there's outages of equipment on the ground or weather. So these are things that we are looking at that indeed do impact the fuel efficiency of aerospace. And then as we get into new technology, our big push is hydrogen, and why it's zero emission. And it's not just zero carbon dioxide emission, it's zero NOx. It is reduced contrails, it is reduced cloud formation. So all the other things that are climate change gases don't happen when you're burning hydrogen. And I don't need to talk to this group about all the issues and why you want to be using hydrogen. But I will point out that, as you've heard, it has 3 times the energy density of jet fuel. But the issue is it takes up 4 times the volume. And volume is very, very important. Volume means weight. Weight means inefficiency. So when you actually are trying to take these up to the 30,000 plus feet, those are very, very important. And those are going to be the challenges for aviation. We see hydrogen being used 3 primary ways within aviation. One is just direct hydrogen combustion. You can take liquid hydrogen and put it into a jet engine today, and it's going to burn. The Air Force did that on a B-57 bomber back in 1955. The Soviets took a Tupolev, I think 157 or something, and they converted it to run on hydrogen back in the late 80s. These are not new technologies, they exist. And they can be, we can take an engine today and optimize it for hydrogen. Of course, the other option that we've heard a lot about is using hydrogen for fuel cells, converting the hydrogen to electricity, and then running electric motors for propulsion. And then the third is using hydrogen to actually make synthetic aviation fuels, not using sustainable, the bioproducts and other resources on the ground, but actually using hydrogen along with carbon dioxide pulled straight from the air and creating those hydrocarbon chains that can create synthetic aviation fuel. So that's the three ways to use hydrogen in aviation. The challenge is, I think we've talked about it, the technology exists, but we have to really bring the weight and the cost down for it to be suitable for aviation. You know, I think we've heard from people over the last 2 days, you know, availability, cost, they're coming down, you know, availability is coming up, costs are coming down. We see that being not just an issue, but something that's going to be taken care of. Infrastructure absolutely is an issue. And of course, regulatory acceptance, not just on the regulatory and certification issues, but of course, passenger acceptance as hydrogen-powered aircraft are introduced. So Airbus, late last year, introduced 3 concept aircraft, which we are calling our Zero-E. You can see the top one looks like a standard or traditional tube and wing turboprop aircraft. Holds about 100 people, goes about 1,000 miles. On the bottom is a turbofan aircraft, again, tube and wing, 2,000 miles, about 200 people. And then in the middle, you see this blended wing body. Again, it's 2,000 miles, 200 people, but it takes advantage of some real advanced aerodynamics, and optimizes how you would put fuel on board such an aircraft. The turboprop and the turbofan on the top and bottom, if you look, the back part of the aircraft doesn't have any windows because that's where you would put these cryogenic fuel tanks that would hold the liquid hydrogen. So you lose a little bit of the capacity inside the aircraft, whereas the blended wing body has a better way to store and distribute the weight and the cargo in that aircraft. So those are the 3 that we've initially talked about. Matter of fact, if you look at the tube and wing designs, one of the things you'll notice is the wings don't look quite the same. And if you're not putting fuel in the wings, you can optimize the wings aerodynamically so that they are even more efficient than the wings we see today. They're probably higher aspect ratio, they're longer, they're thinner, and they give you better lift per unit weight. So these new aircraft would not just be new power systems, they would be entirely new aircraft taking advantage of advanced materials as well as aerodynamics and artificial intelligence. A little bit about the engines on these. They are hydrogen hybrid fuel cell electric engines. A big mouthful, but what it means is we're taking the liquid hydrogen, burning it directly in the gas turbine, whether it's a turbofan or a turboprop. But that engine, that turbine is optimized for cruise. But you need more power than just the power of cruise to get up to altitude for takeoff or aborted landings or all that. So in that case, we have an electric motor on that engine to help the turbine get more energy that is necessary for climb. And the power from that comes from fuel cells. So we have the liquid hydrogen direct to the turbine, some of that going through a heat exchanger, powering a fuel cell, creating electricity, and having that electric motor for those climb and boost situations. Oh, and by the way, a point here is that fuel cell now can provide all the electrical power for the aircraft. And where we have in today's aircraft, an engine has generators or alternators, it has pumps, hydraulics, and all these different fuel systems on it. You don't need to do that when you have a fuel cell providing enough electricity to run all those systems elsewhere on the aircraft. So the gas turbine is optimized for the cruise space. Another aircraft that here's another concept. This is what we call the pod. And in this particular image, it shows 6 of these pods. They're completely interchangeable. And each pod is a complete propulsion system. It includes liquid hydrogen fuel tank, a heat exchanger, a fuel cell, all the electronics, an electric motor, and a propeller. You note there's something different here. I did not say turbine. This is a fully electric pod that would be a complete fuel system. And you could design the aircraft. Some might have 2, 4, 6 pods, depending upon what your mission is and what the design point is for that particular aircraft. So a project we just announced last week is looking at this fully electric system. And the point, we did a project over the last several years where we were looking at high power electric motors for aviation. And one of the issues you have when you bring these particularly high voltage systems up to altitude is arcing. You have great losses due to the amount of power running through, quite frankly, massive cables. So the Ascend program uses superconducting power systems and cryogenics to keep those systems running at optimal efficiencies. So you could use the liquid hydrogen to actually cool the system so that you get, bring the voltages down from like 3 kV to down to 500 volts. And now you can reduce those losses due to thermal issues and become much more efficient. And we're running this program. It's actually been going on for a little while. We just announced it last week. And we're going to be building a demonstrator, which will be running in our test cell to verify this system as we make the determinations of how we move forward as we are shooting for that 2035 entry. I'll get to the timelines in just a moment. So here's our path to zero emission. We are looking at a variety of different technologies, different pathways, different aircraft configurations to determine not only what is going to be best, but what is feasible and what can we get to the market that our customers, the airlines, will use and can carry passengers and cargo anywhere in the globe. But we're looking at everything. It's not just about the climate impact. It's what is the potential for the aircraft design? Of course, maintaining all the safety levels that we have today, maybe even going up another level, looking at how do you maintain the aircraft, how do you industrialize and build these systems, operations, market, infrastructure, ecosystem, all those different abilities that go into operating in the aerospace. Those will all go into the evaluation that we have for this next generation aircraft. And obviously, we are not doing this alone. We have a whole lot of various stakeholders, collaborators, and even some of the folks that you've heard over the last couple of days we're working with. Aerospace doesn't sit in the world of transportation alone. And we're learning and we're contributing to rail, to ground, to surface transportation, heavy duty. So all those are going to work together to build an ecosystem that will support all of these various modes of transportation. One of the ones I want to talk about here is we see an opportunity to use airports as hydrogen hubs. You can block out the aircraft, which won't show up for several decades, but think about all the other things that happen in an airport, is all the ground logistics, whether it's the equipment in an airport that's supporting those actual airplane operations, right, from baggage carts to tugs, but then all the ground transportation, the buses and the cabs and all the vehicles that go in and out of airports. You could use the airport as that hydrogen refueling station. And think about all the logistics, all the cargo and the trucks that are coming and going. And of course, heating and power and all the other things that happen, not just at the airport, but at the infrastructure, the industry around those airports. And then when you bring in the airplanes, now you've got a hydrogen ecosystem ready to support it. So there's a lot of things that we're looking at. This is actually, several studies are going on in Europe, looking at some specific airports that we see them converting to hydrogen hubs within the next decade. So here's our date. We launched the Zero E program back before the pandemic. We've been working on this for some time. We were looking at electrification of aircraft, we've been looking at all sorts of different options. And we've settled on hydrogen for many of the reasons, not only that I've talked about, but as others have shown over the course of this workshop. We made a public announcement of it last year, and we're in the phase right now where we're spending the time not only finding out what is feasible, what is possible, but making sure that they are going to be ready for use. And in 2025, we're going to make a product selection. What is the configuration going to look like? What's this aircraft going to be? And we're going to go ahead and launch it. And so we've got this time period right now to answer all the questions. And we're going to drive the stake in the ground in 2025. We're going to start designing the aircraft, going into the working the supply chain, the industrialization, and start building those first prototypes coming off the line, work through certification issues, and then with the goal of 2035, having an airline enter these aircraft into their regular service. Of course, it's going to, as that earlier chart, it's going to take time. It's going to take decades to slowly not only replace, but supplement the existing fleet of airliners that are now going to be zero emission. So, I've hopefully given you about, I don't even know how long I spoke, as quickly as I could. Here, the charts will be available, but we firmly believe that aviation can be completely clean and supporting all the climate goals that have been set and put out in front of us. So I thank you for your time. Look forward to your questions.
Thank you so much, Amanda. Very inspirational, all the cool tech that is going to be emerging in the future. Very nice. All right, so why don't we continue moving forward with the program, and we'll be please continue to pop any questions into the Q&A box, and we're collecting those, and we'll have an oral discussion on those as soon as we're completed with our presentations. Next is Jeremy Baines, who's the president of Neste US. Jeremy, you ready to rock?
Yes, thank you. Let me see if I can get my presentation up. Okay, do you see that?
We do indeed, looks good.
Okay, well, thank you, Tom and Stanford University for inviting me to this discussion to talk about heavy duty transport. And I'm actually looking forward to talking with you about one of the hardest. Following up in Amanda's footsteps, I'm going to be talking to you about planes. But first, my name is Jeremy Baines, and I'm the regional president of Neste US. And Neste has really had a transformational journey. I think for the first 60 years of our 73-year history, Neste was a Finnish fossil fuel company. But since the early 2000s, Neste has really transformed into one of the world leaders in renewable fuels. And when we talk about renewable fuels, Neste is organized in three different businesses. The renewable road transportation, so everything that moves on the road, and again, focus would be on the heavy duty sector, those really hard to abate segments of the transportation industry. The second one is renewable aviation, and that's what we'll spend most of the time about, but then also renewable polymers and chemicals. So all the plastics that you have in your hands today, that goes into cars, that goes into planes, we are also working on how do we make those more renewable? How do we make those more sustainable? And one of the cornerstones of this is really the circular economy. And we can look at circular economy in different ways. One way, which is very concrete, is an example case that we have with the city of Oakland, where we collect the used cooking oil from the restaurants in the Oakland municipal area. We convert that, in this case, into renewable diesel, and it powers their municipal fleet. But we're now also starting collecting used cooking oil from Dallas, Fort Worth, and many other airports, with the aim of converting those into sustainable aviation fuel, which can power planes. And if you think about circularity in the broader context, and we heard some examples of it today, it is also taking the CO2 out of the atmosphere that is there now and converting them back into a fuel that, once it's burnt, is just putting the CO2 back in the atmosphere. So you are continuously recycling what is in the atmosphere. And actually, you can get to the point that you sequester some of that CO2 so that you're actually taking out CO2. So you're continuously borrowing from the atmosphere rather than adding to the atmosphere. And just to put this into context, Neste has two very concrete climate commitments. One is our carbon footprint, and we are committed to reaching carbon neutral production at all of our facilities by 2035. And why is that important? In the renewable fuels that we make today, they are actually net zero emission fuels. All of the carbon that is in those fuels was carbon that was previously in the atmosphere. The only additional carbon is the carbon that is used in the manufacture or the transportation of those fuels. So with our goal of reaching net carbon production by 2035, we will be taking away that greenhouse gas emission from the production of the fuels. And then over time, as the transportation becomes more efficient, as our fuels become more efficient, we get closer and closer to a net zero emission fuels, with even the potential of getting to a negative carbon emission fuel. And then the other one is our carbon handprint, and that is how we work with our customers to reduce their emissions. Currently, we're reducing the emissions for our customers by about 10 million tons per year, and our ambition is to get to 20 million tons of carbon reduction per year. Now, I had promised I would talk to you a bit about sustainable aviation fuel. I think one of the important things, the main takeaway, if you want, from a sustainable aviation fuel is that it exists today. It's in use today, as we heard Amanda saying, hundreds of thousands of flights are flying on it already today. And it works safely in existing aircraft and airport infrastructure. So we don't need to change anything. Everything that is everything that we're using today, from the mechanics to the planes, to the airports, to the infrastructure, will work on sustainable aviation fuel. And Neste and Airbus actually are partnering as we speak on testing 100% SAF safely in airplane engines today. So while we wait years, maybe several decades before other solutions like hydrogen come along, we already have a solution that today will reduce emissions from airplanes by 85% or more. And not only the climate emissions, but also the other pollutants from that. So this will then directly impact the communities living around the airports as well. And then what's it made from? Well, today we make our sustainable aviation fuel from fats, oils, and greases, but renewable ones, not crude oil. I think that's the important difference. And today we use 10 different feedstocks. Our favorites are waste and residue materials. Think used cooking oil, think grease, rendered fats, stuff that you would find in large container bins behind the dining halls at Stanford. These are raw materials that contain carbon molecules that were previously in the atmosphere. So we're really just reusing what's in the atmosphere. And why is that? So the mechanics around that are pretty simple. You've got carbon dioxide in the atmosphere. The plant inhales that through photosynthesis, stores that energy in the seeds. It can be extracted as a vegetable oil. We can convert that vegetable oil into a renewable fuel. Once it's burned, that CO2 goes in the atmosphere. It's a closed loop. Yeah, so there's no new CO2 that comes in the atmosphere for that. And because these carbon chains are very pure to start with, they are, remember actually the first diesel engines were meant to run on vegetable oil, so they are the perfect molecules to start with. We just tinker with them so that we make them even purer, so that they've got the right hydrogen balance to carbon. So they are very pure hydrogen chain. They burn very, very purely, and therefore they are very efficient. They are very efficient in land transportation. They are very efficient in aviation, and these molecules are very efficient when you make polymers and chemicals out of it, because you're starting with the right length. Yeah? And so all these things are true, whether it's for aviation fuel or sustainable aviation fuel. And then this is not the end of the feedstocks that are available for renewable fuels. So I talked about the lipids, the fats, oils, and greases, but under development is a whole host of new generation renewable fuels. And these will be carbon neutral, maybe even carbon negative fuels. And you need to think of algae, municipal solid waste, forestry waste. And algae would be able to be grown, farmed in ponds on land which would not be suitable for agriculture. Municipal solid and these algae, excuse me, would then be crushed, so it would be a source of protein and a source of oils for fuels. Then another route is municipal solid waste. This is not a fatty acid, not an oil route, but you would convert, you would combust it and collect those hydrocarbons and then convert those into fuels. Then there's forestry waste. There's trees being harvested continuously for paper and for pulp and for wood, but the tree tops, the branches, the bark, etc., they are discarded today. Those can be converted into fuels. And then we talked today, there was examples about renewable electricity and how you can capture the atmosphere out of, capture the carbon dioxide out of the atmosphere, and those are the power to liquids. And really, if you add up all of these sources of renewable energy, there's really a large amount of feedstocks out there to be able to convert us away from burning fossil fuels. And in terms of production, so today Neste is one of the largest producers of sustainable aviation fuel. This is a new industry, a relatively new industry, I should say. Neste has been producing renewable fuels and researching it for over a decade, but it's also a very fast growing industry. And Neste is expected to produce 15 times more sustainable aviation fuel in 2023 than we produce today. And this number will keep expanding as Neste continues to invest in renewable production, as we continue to expand those, and as we build new ones. And there's not much secrets in organic chemistry. And our industry peers and some of the other fossil fuel players are also looking at this and very rapidly ramping up their production as well. And we're talking about some of the oil majors that are looking at that in the United States and in Europe. In the United States, we have the likes of Phillips 66, of Valero, of Marathon, of HollyFrontier, of CVR, big players that are looking to convert into renewable fuels. But then Neste is also partnering with a lot of these oil majors like Shell and BP to make sustainable aviation fuel more available and bring it to the market much faster. I said that this is fuel available today. Just a couple of examples. So we've been partnering with, for example, American Airlines, and we are an industry-leading sustainability agreement with them. They are really looking for ways to reduce their emissions for their customers. San Francisco Airport, it's been really what they have called a climate quantum leap. We are now, because sustainable aviation fuel is a drop-in solution, we have been able to overnight practically start putting sustainable aviation fuel into all of the planes that are leaving from the airport. So it is now readily available for cargo, for commercial, for business aviation at the airport. And Neste and our partners are expanding that to very many airports in California and then beyond, just as we are in Europe and in other regions. And another example is signature flight support. This is a serves the private aviation customers in FBOs across the country, and they are now allowing their passengers to fly with a much smaller carbon footprint than in the past. And I think this is one of these things that we see coming up from the customer level. It's the customers really demanding that the airlines provide sustainable solutions, in a safe and efficient manner. Neste, for example, recently announced that all business travel from the Neste employees will be compensated through sustainable aviation fuel. And I'd like to talk to you maybe a bit more about the oil demand today. And as Cristina Figueres, the former UN Executive Secretary for Climate Change, once demonstrated, we really need to halve all greenhouse gas emissions by half by 2030, then halve again by 2040, and halve again by 2050. So we need to start reducing the emissions now, not hope for something further down the line, because every molecule of CO2 that we put in the atmosphere today will be around for centuries to come. And this is data that Neste has put together based on world energy and a number of other scenarios. With world oil consumption, let's call it 4.5 billion tons per year, of which the global oil demand for transportation is about 2/3. Then we start seeing what electric cars could do. Then we see what global biofuel consumption was in 2018 and what the potential is. And then we look at what is the scenario if we were to double electrification. And you see that what it actually says is that the decarbonization challenge is huge. And we need all the solutions. We need the electric cars, we need the electric planes, we need the hydrogen, but we also need the renewable bio-based fuels and the renewable fuels, which are already contributing very greatly to carbon reduction today. And we really see that low carbon fuels are scalable. It's a solution that works and really greatly can contribute to reducing greenhouse gas emissions. So we need to use that potential. And what is needed, and I think this is similar to what we heard in the first speaker of this panel, is we need clear policy support for this. We need clean fuel standards. This really incentivizes the production and the use of renewable fuels. But it has to be really grounded in the life cycle analysis, because cost is really a big part of this. So we need to have a market-based, technology-neutral price on carbon per sector, because not all sectors really have the same cost to decarbonize. A light passenger car is relatively easy to electrify, whereas there are no electric cables long enough to power a plane. Yeah. And we also need to recognize that renewable fuels may never be cheaper, but then at the same time, fossil fuels may no longer be acceptable either. So we need to understand what is the true cost of carbon, and will it really be justified in 10 years, 20 years, 30 years from now for us to continue to be burning fossil fuels in planes? I think the answer is clearly no. So we're excited about planes flying more and more on sustainable aviation fuel. We're excited by seeing corporations wanting to join this movement as well. I'm pretty sure that we will also see from the individual side where we make choices to fly on maybe an Eco Plus seat alongside an Economy Plus seat. Yeah. And then in terms of policy, yeah, to maybe balance out that cost differential, having those types of incentives like a sustainable aviation fuel blenders tax credit, which would really then help support the production, making it more available, being able to transport it across the country and work safely and efficiently in airplanes. And that's the presentation that I had for you today, and looking forward to answering any questions that you may have at the end of this. Thank you.
Outstanding. Thank you so much, Jeremy. Wonderful. So super. Let's go to our last speaker if he's available. I know that there was a little bit of a time conflict. Toru Sugiura, are you by any chance ready and available to give your presentation at this time, or we could take it after the Q&A?
No, I'm here. So thank you.
Fantastic. Well, just as a word of introduction, Toru Sugiura is the Senior Manager at the Corporate Strategy and Business Development Division at Toyota Tsusho America, and the floor is yours. Thank you so much for being with us today.
Thank you very much, Thomas. Yes, thank you. My name is Toru Sugiura from Toyota Tsusho America, Los Angeles office, and I'm in Sustainable Business Development Department. I just wanted to make sure that our company, Toyota Tsusho America, is a group company of Toyota Motor. So we are a separate company of Toyota Motor. So we don't manufacture or we don't sell vehicles, but as a group company of Toyota, we support Toyota manufacturing and other business development projects. So we are currently working on this hydrogen society development, mainly supporting infrastructure part of that project. So today I would like to discuss about fuel cell port equipment and hydrogen mobile refueler feasibility study and demonstration project that we are currently doing it. Okay, so I would like to present my fuel cell port equipment and hydrogen mobile refueler feasibility study and demonstration project. We, Toyota Tsusho, are currently conducting feasibility study and demonstration project at the Port of Los Angeles. What it is on this left side cartoon-like diagram from production, actually energy source to hardware equipment, all combined together feasibility study and demonstration project. We have invested a biogas production project in Central Valley, California. It's a dairy farm biogas renewable natural gas project. We'll inject the renewable natural gas to utility pipeline and extract it, the RNG near the Port of LA, our hydrogen production site. And we are going to load the hydrogen to our newly developed mobile refueler, such as a concept picture on the screen. And we will supply the hydrogen to port equipment, which we are converting one diesel top handler with our Toyota fuel cell system. So with this, all this, we try to have a value chain system from upper stream to lower stream using application. And once this feasibility study and demonstration is successful, we would like to move forward with another equipment that is believed to be suitable for port equipment with fuel cell systems such as yard trucks or rubber tire gantry crane, RTG, and some dryage trucks. Once these are successfully implemented, we would like to reach out to different ports of the United States as well as worldwide ports. Just to elaborate a little bit more on our hydrogen value chain concept is that currently we have an experience of operating hydrogen station business in Japan, which just by hydrogen station by itself, the business model wise, it's not very economically viable business model. So for United States, we try to put all this value chain combined as a one business model from upstream, energy source, production, storage, distribution station, and market creation and environmental project all together to create a synergy business-wise, but also try to generate supply and a demand at the same time. One of the common challenge we hear when we talk about hydrogen society is, okay, who should come first, hardware or hydrogen supply? So it's always chicken and egg discussion. So we try to create those demand and supply at the same time so that hydrogen society will come soon and accelerate this market demand. And again, I explained we invested a biogas project in Central Valley, California, and we are also building a small decentralized hydrogen production hub near Port of LA, so we don't need to transport the hydrogen very far, which transportation cost is the main cost of today's hydrogen cost structure. And we are newly developing hydrogen mobile refueler mimicking diesel refueler truck by the request from port terminals. And we can use that mobile refueler as also station application, but for this particular demonstration purpose, the mobile refueler is gonna go directly to the port terminal. And we are working with the port terminal and also equipment OEM to install our Toyota fuel cell system so they can test out fuel cell system with their equipment. All of this project by itself should support environmental projects such as Port of LA and Long Beach Clean Air Project, as well as Toyota Environmental Challenge. So looking at the Port of Los Angeles and Port of Long Beach area, according to their port equipment inventory list, you can see on the left side, this is a list of port equipment list, LA and Long Beach. As you can see, many equipments, nearly over 3,000 vehicles and equipments are working in a port area, and most of them are operated by diesel fuel. And after extensive hearing with the terminal operators, we have identified with this red star marking that those equipments is likely or suitable for hydrogen fuel cell technology. On your bottom right side, we have estimated potential hydrogen consumption for those equipment, such as top 100 RTG yard truck. These equipment are estimated to use quite substantial amount of hydrogen compared to passenger vehicle. For example, Toyota Mirai can take up to 5 kilograms, but those equipment can use 5 to 10 times more than that quantity per day. And on top of that, the dryage trucks that are coming in and out to the port area daily basis, which is about 13,000 trucks, they also estimated to use 20 to 30 kilograms of hydrogen per day. So we figured that the port area is probably the market potential hydrogen market that will come high demand quite soon. As you can see here, the Port of LA and Long Beach, there's a zero emission goal by 2030. All equipment must be zero emission, and dryage truck to be zero emission by 2035. So those goals are also pushing port terminals and fleet operators to think about the technology transition. Talking about this demonstration unit Top 100, which is a very huge version of forklift equipment that moves a container to a container yard to dryage trucks. And actually there are already a few demonstrations going on at the Port of LA for this Top 100 zero emission project. The one on the left is a Top 100 from manufacturer Taylor. They have converted this Top 100 from diesel engine to completely battery electric type, carrying 1,000 kilowatt of battery. And the middle one is a high-style demonstration units that has a battery and fuel cell hybrid combination version that has 350 kilowatt battery and 27 kilograms of hydrogen tank. And our demonstration unit is on the far right, which is a fuel cell dominant system, which we have 60 kilogram hydrogen tank and a very small 85 kilowatt of battery. Each demonstration unit has a different characteristic. And so for the port terminal and also port authority, they are interested in watching these different demonstrations to see which one will be most suitable, economically and environmentally viable project. And the advantage of our fuel cell dominant system is that basically this Top 100 will be operated by hydrogen only. So there will be no need of battery charging infrastructure at the port terminal. So which will be quite challenging for other demonstration, which requires for this middle one, high-star demonstration requires both battery charging infrastructure and also hydrogen refueling infrastructure. And the battery electric type, full battery electric type, only the far left one, requires a very large infrastructure for battery charging and might require very small power plant type infrastructure once all the Top 100 will become battery based. And also charging time is quite long hours. So we will see which one is going to be most suitable technology. And this is a port air emission inventory report. And as you can see on the under red line, RTG crane, top 100, and the yard trucks, which we think that most likely will convert it with a fuel cell system, is the high pollution vehicle equipments. The top 100 we picked for our demonstration actually emits highest NOx emission, and also CO2 wise one of the highest. So it is very important that these equipment will be converted first. And all of the port terminals that we did hearings, they want those equipment to be converted to zero emission as soon as possible. As you can see in California, the hydrogen or zero emission motivation is very clearly important. And as you can see by port area 2030 for all equipment must be zero emission, and truck wise by 2035. And the recent CARB announcement of zero emission, ZEV truck rule also pushing drayage truck fleet operator to consider implementing zero emission trucks. So we are targeting particularly this port area as the market that needs to come sooner than any other areas. Even though the port terminals port equipment goal, zero emission goal is 2030, and drayage truck goals to be 2035, when you see this equipment and also truck inventory report, many of the equipments, if you look at the port equipment on the left side, RTG average model year is 2009, top 100 2012, yard truck 2011, and drayage truck wise, a lot of about 13,000 inventory, about 8,000 are actually about 2007 to 2009 model, which means considering those equipment needs to be renewed in about 13, 15 year cycle, they are actually about to, they need to be changed to new version. So all terminals and drayage fleet operator, after our discussion, they said actually they need to renew their trucks and equipment actually sooner than this port goal of 2030 or 2035. So our demonstration can be very important to prove of the concept that the performance of fuel cell equipment and trucks are similar to the diesel equipment and trucks, so that we can gain their trust for their consideration of this zero emission technology transition. From Japan, we have extensive experience for hydrogen. We have several demonstrations going on at this moment for wind power to hydrogen, solar power to hydrogen, and biogas to hydrogen demonstration. And we also operate 8 hydrogen stations in Japan. So we want to use our experience to succeed our demonstration in the United States. Lastly, the story is beautiful, but there are tons of challenges to overcome. First of all, hardware commercialization by OEM, especially port equipment OEM. The zero emission goal is currently mainly coming from LA area only. So port equipment OEMs are still not very willing to develop and mass produce zero emission equipment very aggressively. So we need to make sure that we need to communicate with them for the needs of this equipment from OEM side. And also cost gap from current scheme. Unfortunately, the hardware infrastructure and hydrogen fuel itself, compared to diesel, it's much more expensive still, maybe twice or 3 times more expensive. So, you know, our demonstration is okay, but after demonstration, how we can reduce this cost so that the user of the equipment will be comfortable switching the technology. So that's also a challenge. And also regulation adaptation, particularly refueling protocol and fire code and permits. Particularly fire code, if we try to operate hydrogen mobile refueler at the port area, there must be fire code approved, which takes quite long time for the approval. So this type of regulation also needs to be adopted soon so that when hardware and infrastructure is available, regulation is not going to slow down the process. Lastly, the user education and training is crucial because when we talk to fleet operators and port terminals, the first thing they say is hydrogen safe? So we wanted to make sure that all these hydrogen equipment and trucks are safe to operate and can perform similar or even better. Actually, in terms of noise-wise, obviously fuel cell system is much quieter than diesel engine system. So we need to make sure that we educate the users so they feel comfortable moving towards this new technology. So we will need a collaboration from all stakeholders. That's the key for this technology transition success. That's all for my presentation. Thank you so much.
All right, thank you so much, Toru. And I'd like to just take a moment and let's thank all of our panelists today who gave absolutely outstanding presentations and that educated me so much in this space. So wonderful. Let's transition to the Q&A portion. And I thank all of you who've been posting questions in the chat. Some of them have already been answered by our panelists themselves who've typed out responses. So let's look into the ones that are open, and I encourage people to continue asking questions if they'd like. Popping them into the chat. So maybe we can start with you, Toru. We'll go a little bit backwards, since you've got the mic. And one of the questions that was asked is, where will the large mass of hydrogen required for these ports, the ports of LA and Long Beach, to be stored? And in what phase? Will it be compressed or will it be liquid? It says here in the chat that the neighborhood of Long Beach ports has been very much opposed to any large-scale storage of flammable fuels. How will you overcome this?
Yes, that's a very, very excellent question. That's the challenge we need to overcome. And at the initial stage, our mobile refueler should be able to support the port terminal equipment refueling. But if these yard truck, which just one terminal might have 100 yard trucks and then maybe 50 top hundreds, and their refueling window time is only between 4 a.m. to 7 a.m., the 5 hours. So that is the mass refueling at the simultaneous refueling is a challenge. So the liquid hydrogen solution is also one of the potential, but also we are considering potential pipelining from nearby hydrogen production to the port terminal area. Just a multiple mobile refueler going back and forth. That needs to be still studied, and we need to figure out. That's an excellent question, yes.
Thank you so much, Toru, for that response. And can I ask all the panelists if they don't mind just getting their video up and running? So we're going to be passing the ball here to a number of you with different questions. Let's go back to Rasmus's presentation at the start. There was a question that was asked regarding green ammonia. And so green ammonia was mentioned, green methanol was mentioned. What about other renewable fuels like dimethyl ether or renewable propane? What are the advantages of ammonia over other possibilities?
Okay, the advantage on green ammonia is the CO2 content by far. It will overrule any of the other transportation fuels that you mentioned. You have propane, LPG. It's about 15% CO2 emission saving versus traditional fuels that you have today. You have ethane. I think there was a question on that as well, C2860. Also a lower CO2 emission savings around ethane, and transportation ships are very expensive. Water breaks down easily. There is corrosion within ethane. And besides, in terms of price competitiveness, when you are in the lower CO2 emission savings, so i.e. if it was very significant compared to green ammonia, price maybe you could compete on price, but there's a price differential where we see the shipping industry being able to compete with the aviation industry, etc., in terms of willingness to pay for products such as ethanol.
Excellent. Thank you so much for that response. Fantastic. So let's move to Jeremy's presentation. There was a question about Neste and the use of unwanted invasive vegetation, such as water hyacinth. Could that be a supplement to the different fuel feedstocks that you were describing earlier?
Yeah, so I think it's a good question. I think today Neste's technology is geared to using organic fats, oils, and greases, and I think one important thing is this is done on an industrial scale. I mean, Neste today uses nearly 4 million metric tons of feedstock. That's about 8 billion pounds of feedstock of oils. So the scale of this is enormous. So harvesting invasive vegetation is probably not going to be able to scale up to the size that we need. Yeah, so there might be other applications for those, but it's today it's really looking at these fats, oils, and greases before we scale up into other feedstocks.
Great, and maybe on that note, since you've got the mic open as well, Jeremy, there was a question about, is there enough theoretical capacity to run all airplanes with renewable fuel? Basically, the feedstocks that you have in mind, how far will that get us before transitioning to other feedstocks, perhaps a direct captured CO2, perhaps one day?
Yeah, I think that's a fantastic question because it comes up very often. And if you look at them in isolation, then you could say that, well, there is not enough. But it's like looking at the first oil well. Nobody expected that there would be horizontal drilling or deep water. So today we're looking at what is readily available, and every time that we look closer, we find more availability of waste and residue. And then once we move past the waste and residue, you've got all the vegetable oils, all the cover crops, all the crops that can be planted on degraded land, and then you go into algae and others. So if you look at only today, then you could say, oh, maybe not. But if you look at what's on the horizon as feedstocks that can be used because they have already been tested, then yes, I do believe that there will be enough renewable fuels of all shapes to replace fossil fuels in aviation.
Excellent. Thank you for that response, Jeremy. So let's turn our attention to Amanda for a moment. A question was asked about green ammonia in aviation. So we heard some strong arguments for maritime use. What about aviation? What are your thoughts there?
Well, we've looked at ammonia, and the issue that we ran into is toxicity of it. And it does not quite have the energy density of just hydrogen. Nor does it's certainly much heavier than hydrogen. So it doesn't have the advantages that hydrogen has, and it has a few of the negatives. And also, quite frankly, there are fuel cells, there are turbines that run on hydrogen today. And as I mentioned, we're looking to drive a stake into the technology availability in the next few years, rather than waiting for new technologies to come around that might be around ammonia. Now, I will say that ammonia might have a place in the hydrogen economy just because it's an easier way, potentially, to transport hydrogen in pipelines. So I'm not counting it out. I'm just saying it's probably not going to find its way into an aircraft.
Great, thank you for that response. Wonderful. So I'm going to bring up, let's go back to Toru for a second here. Another question was asked regarding the ports of LA and Long Beach. In that location, can you say a little bit about the economics? The question specifically says, at what price does hydrogen use become economical? What's the current price per kilogram?
Yes, that's also a very excellent question. Thank you. Currently, for passenger vehicle hydrogen, it is sold between $12 to $15 per kilogram at hydrogen station if you own a hydrogen vehicle. However, the port terminals, after extensive conversation with them and also dry truck operators, they expect hydrogen price to be similar level as diesel, which is they are currently buying diesel $3.50 per gallon. And the equivalent hydrogen price maybe like 550 to 650 range. So another challenge is, even if there's an infrastructure and hardware available, unless hydrogen price will come down somewhere at that range, port operators or dryage truck operators, they won't convert their equipment with hydrogen system. So it is a big challenge how we are going to reduce the hydrogen cost to that the user desired level. So definitely some kind of incentives and maybe grant programs, policy support is definitely important in an initial phase.
Excellent. Thank you for describing some of the details there on economics. No doubt that plays a very important role. Perhaps worth pointing out that because fuel cells are much more efficient than internal combustion engines, so 1 kilogram of hydrogen, you're reporting prices based on a kilo. A kilo of hydrogen is about the same energy content as about a gallon of diesel or a gallon of gasoline. And fuel cells, of course, are about twice as efficient, roughly, the current fuel cells, I should say, versus internal combustion engines. So there's definitely more mileage per kilo than you would get on a gallon of either gasoline or diesel. So something to bear in mind, but still far from where we need to be, and it's all interconnected. Wonderful.
That's correct. That's correct, Thomas. Thank you.
Great. No, thank you. Super. Let's maybe go to some higher level questions here. There was a question posted in the chat about maybe there's a need to account for transformations due to COVID, and how does COVID affect all of this? So I had presented some projections from ExxonMobil that were pre-COVID. Most projections are pre-COVID. Obviously, we're still in the midst of a pandemic. And so a question to our panelists, anyone who would like to share some thoughts based on their industries, how do you all see energy utilization and perhaps sources of energy, the markets changing due to from COVID having happened now? How do those future projections look to you? Any different than what we might have thought a couple of years ago, or is there something fundamentally new? Who would like to take that question first?
Thomas?
Go ahead, Jeremy.
Yeah, I'm just saying that I'm based in Houston. I haven't traveled since March of last year. I can't wait to start flying again. I've seen my house for over a year now, so I'm pretty familiar with it. I think we all want to start moving again. We all want to start traveling again. We all want to start flying again. I think we will very rapidly go back to the levels that they were pre-COVID. And then the big question is, are we going to go back to the same old ways, or do we want to do it in a more sustainable manner? Yeah? Travel is essential for business, for culture, to meet people, to meet family and friends. So we just want to get back to it.
And I will say from the aviation standpoint, what we're seeing globally is that while not as many people are flying, there are about 70% of the flights that there were a year and a half ago. So the planes are flying with less people in them, but they're flying more cargo. And so even though the aircraft are flying, the usage of energy and thus the emissions, if you recall, and I can put this back up on the screen, we've taken into account, or we're looking at the dip that was caused by COVID, but we expect and anticipate that we're going to return to that growth pattern once everyone gets back into the air. And we don't, while that is probably delayed, caused about a maybe 3 to 5 year delay in the implementation, our goal still is to get to that 50% goal by 2050. So the same goals apply. We're just going to need maybe not quite as much SAF as we had anticipated, but we still need to address all the other options. And let me take this quick moment to say, while we talk about SAF, we talk about hydrogen, there are other solutions that are going to be applied to the aerospace industry. And there's going to be all electric battery operated vehicles. There's going to be hybrid vehicles. There are going to be a variety of different solutions depending upon what the mission is. So it's not going to be one solution fits all of aviation, but indeed various solutions that are tailored for the benefit of the economic while reducing the emissions. So it's going to be a variety of all above solutions.
Indeed, and it would seem to me that the appetite for economic growth has not changed a whole lot. In fact, there's probably more of it now than ever. So it seems like there will be continued need for energy, for transportation, for many different sectors, and yeah. So this is a big blip, but yeah, it's a decades-long challenge that we're solving, and yeah, the needs are still there very much. So. Great. Let me go to one more question in the chat, and then we'll bring it to a close. We have about 3 more minutes left in this panel, and I'll be sending it back to Jimmy. And so this is another high-level question of, for many decades, atmospheric CO2 in excess of 280 parts per million has been compounding annually at about 2%. When can we expect this rate to slow down based on the expected adoption rate of all these technologies? Who amongst our panel would like to take that first?
I can talk for shipping then. On a global basis, more difficult on a macro level. Just back to the question before, it's more philosophical, but have we had more time to look at ESG and the importance of reducing ESG? I think basically in the shipping industry, people have had more time to focus on how important ESG is. So in that sense, while oil demand will go above 100 million barrels again per day, it will come, growth will be there. I think the industry have had more time to look at what we need to change. So that's a positive, and that can drive behavioral change over time. About this question, when can we see the peak CO2 emissions, if I can rephrase the question, if that's understood correctly. Shipping, we expect it to produce a lot more CO2. If we get regulation, which I am a true believer and hope, full of hope of, I think by 2030, 35, I really hope we can see peak CO2 from shipping. It's aggressive, it's very aggressive, and it's much more aggressive than the majority. 2035 is the safe bet, I think, but hopefully 5 years before.
Yeah, for aviation, it's about the same. We're expecting in the late 30s, it'll peak and start to drop. But I think it's important really for people like you, Tom, and those in the academic industry, who are looking at those to say when is that going to occur? You look at the chart that you had at the beginning. Aviation is only about 3% of global emissions. Marine is also a small component. It's the heavy duty trucking. It's the commercial and the automobiles. Those are the ones that really have to see the adoption of zero emission vehicles to start bending that curve for the entire atmosphere.
These are really good points indeed. Maritime and aviation are some of the most difficult segments to decarbonize and perhaps the slowest of the ones that were mentioned. Passenger vehicles are much faster in that way, much more nimble and much more agile. But I have to say that this session has given me a whole new sense of optimism for these very difficult to decarbonize industries. Thank you, all of you who've shared your insights into these different industries that all work together, and certainly some big challenges ahead, but also wonderful opportunities. And a few percent might not sound like a lot, but when you're emitting over 40 gigatons of CO2 across the globe per year, a few percent of 40 plus gigatons is actually quite a few gigatons, and we'll take every bit that we can get. So one more round of applause. Thank you all to our panelists. Great presentations, great discussions. Thank you to all the participants, the people asking questions. Hope this was as informative and educational for you as it was for me.